Why does time dilation occur near light speed? To answer that question, we have to first ask another, what is time dilation? Simply put, it is the difference in the passage of time between two observers who are in relative motion with respect to each other. For example, if you were to travel near the speed of light, and then return to Earth, you would find that less time had passed for you than for someone who remained on Earth. That is because time is relative and it slows down for objects that are moving at high speeds. But why does this happen? Why does time slow down near light speed? The answer lies in the nature of space-time itself. Space and time intertwined in a four-dimensional fabric are relative to the observer's frame of reference. This means that the passage of time is not absolute. It is not the same for all observers. It depends on the relative motion between the observers. Imagine two observers, one on Earth and the other on a spaceship traveling at a high speed. The observer on Earth sees the spaceship moving by while the observer on the spaceship sees the Earth receding away from them. Each observer measures time differently. This is because as the spaceship accelerates to high speeds, the following phenomena occur. First, the gravitational field around the ship becomes stronger. Second, the length of the ship in the direction of motion appears to contract. And third, the passage of time itself slows down. These effects are all predicted by Einstein's theory of special relativity. The reason why these effects occur is due to the constant speed of light. No matter how fast the spaceship is moving, the light inside it always travels at the same speed, regardless of the observer's frame of reference. This constancy of the speed of light leads to the counterintuitive consequences of time dilation, length contraction, and gravitational time dilation. Now, let's try and understand why only light can travel at the speed of light. All objects have mass and energy. The equivalence of mass and energy is given by Einstein's famous equation E=mc, where E is energy, m is mass, and c is the speed of light. Since the speed of light is constant, it follows that the energy of light is also constant. This means that the mass of light must be zero, otherwise its energy would change as it moved from one frame of reference to another. Since light has no mass, it can travel at the speed of light without any energy expenditure. However, an object with mass cannot travel at the speed of light because as it approaches the speed of light, its energy would increase infinitely, which requires an infinite amount of work to achieve. Therefore, nothing with mass can travel at the speed of light. Only massless particles like photons can travel at the speed of light. If you were to plot a graph of energy versus mass, you would get a hyperbola. As the mass of the object approaches zero, its energy also approaches infinity. Conversely, if you take an object with a large mass and accelerate it, its mass will increase, leading to an increase in energy. If you continue to accelerate the object, its mass will eventually approach infinity, and the energy required to accelerate it further would also approach infinity. This means that an object with mass cannot travel at or faster than the speed of light. Now, if you were to travel at near light speed, your mass would increase significantly, making it very difficult, if not impossible, to travel even faster. In fact, as you approach the speed of light, your mass would approach infinity, meaning that you would require an infinite amount of energy to accelerate beyond that point. This is why it is impossible for anything with mass to travel at the speed of light. So there you have it, the scientific breakdown of why time dilation occurs near light speed. It's all about the constancy of the speed of light and the equivalence of mass and energy. At near light speeds, the energy required to move an object with mass increases dramatically, leading to a corresponding increase in mass. This increase in mass makes it very difficult, if not impossible, to accelerate beyond that point. Ultimately, it is this fundamental property of the universe that gives rise to the mind-bending phenomenon of time dilation.